Wow, what an act to follow. Joe was hugely, wickedly inspiring. It's really amazing to see how a company like SpaceX has gotten to where they are today, and really, I think, inspiring the whole, at least our whole ecosystem. As I think some of you are aware, yeah, Europe has a little bit of ways to go to kind of reach where he is and they are at SpaceX and Tesla. We will be inspired, and I think we'll take a lot of guidance, I think, and some really good ideas from what was just presented. So yes, ClearSpace. What do we do? Who are we? I'll do the best I can to kind of bring you a little bit into the narrative of who we are, where we come from, what we're doing, where we're headed. So what you see in front of you here is, it's a relatively close artistic representation of what the ClearSpace 1 spacecraft and mission is all about. So what you see on the right is the target. It's a Vespa upper stage launch vehicle adapter, 150 kilogram adapter that was launched back in 2013. One of multiple thousands of masses of debris, basically junk, that are up there that have served their purpose and essentially now are defunct, either just from their very nature, from our unfortunate inability to actually plan sustainably throughout the years when we approach space activities and missions. But nevertheless, anyway, something that has served its purpose and now no longer is. So as I said, tens of thousands of similar objects are like that up there. And what you see on the left is what we're currently developing, the ClearSpace 1 spacecraft, i.e. a servicer and a capture system. So what looks a little bit like a spider are the arms that will essentially capture the Vespa and close and then deorbit both as a stacked element. So what do we do? Yes, we basically shape sustainability beyond Earth. That's a huge statement. It's a huge mission. But as I state, we go there. We are going there. We are developing this as the world's first system that is designed to actually capture a non-cooperative target. Non-cooperative targets being elements that are not designed to actually receive a paired or an approaching vehicle, so to speak, in this manner. For example, there may be OneWeb, for example, has a system, a docking feature on their spacecraft that a servicing vehicle can actually come up and dock, so a cooperative element. Most of what's up there are clearly non-cooperative. This happens to be in the LEO belt. We're addressing LEO, potentially MEO as well as the GeoArc assets. Before I continue, thank you so much, Marco and the Valley Space crew. This is really an honor, and I'm really humbled to be here today. I've been invited for this, and just really among a lot of wonderful people and just really sharp minds. So really count myself inspired and honored to be here. So yes, right, sustainability transcends Earth's boundaries. We, for years, have kind of not necessarily respected a lot of our ecosystem, our environment, again, for various reasons. We didn't know better 50 years ago or 100 years ago, and very slowly here, unfortunately, it's a little bit slower than we'd like. We are beginning to address these challenges, be they in the oceans, be they in garbage dumps, be they mineral resource extractions, et cetera. But one thing that's evident, which was one of my dreams when I was 12 years old, was to actually have this view one day from a window somewhere, right? 12 years old, I didn't know where that was going to be. But this effect, right, the overview effect has enabled, essentially, I don't want to speak for Livingston, he's experienced it, but I think it is an effect that all of the astronauts that have viewed our Earth from above with its super thin atmospheric barrier protecting us, have this emotional response that, as it's been described by a couple of astronaut friends of mine, drive them to bring as much as they can of improvement, of betterment, so to speak, however we want to define that, to our Earth, to this fragile planet. So what we're in the process of doing, really, is taking our approach, our, if you will, perspectives to how we have, many of us within the team, addressed recycling, reuse, sustainability, etc., on Earth into orbit. So, as some of you might know, there are a lot of abandoned, defunct pieces of junk, essentially. I'll just call them what they are. Satellites and rocket bodies are essentially make up the vast majority of the large elements that are up there. They're abandoned, yes, they served their purpose, but now they no longer do. And they are literally clogging up our highways, be they in LEO, MEO, and even sometimes in GEO, there are some issues that, that have come up that are being addressed. Every year, there are more, there's probably 75, maybe a few more objects per year that are being added to this environment. So this environment, I mean, is our commons, right? The commons principle dates hundreds of years ago, commonly used public space. This is where we're headed. So granted that each one of those dots, maybe we can go back and try it again. Granted, each one of those dots is represented, obviously for visual purposes, is larger than each one of those objects, but nevertheless, it does give you a bit of a, oh, I don't want to say frightful, but a very, some sensitivities as to what it is exists today, and kind of considering, as you see on the next chart, where it is we're heading in the very near future. That future is going to be among us very, very quickly. We need space today. So this just goes back, say, to 2017. The addition of new missions, systems, spacecraft, et cetera, that help us do all kinds of things, right? Make phone calls, connect to our loved ones, families, work, dial in, via Teams, Zoom, et cetera, from wherever we are in the world to wherever else we need to be. We're in 2022. Okay, things are beginning to increase a bit, and recognize that most of everything that we do in space is right here. So there are vast domains of free space, but those are areas that don't necessarily lend themselves to hosting what it is we're going to be using further down this, further downstream. So we need the space today, which is clear. Very soon we're going to need more space. How do we do that? It's just it's a kind of a phenomenal representation, because very shortly it just is completely covered, it's blanketed. So that's the reality that we're in today. We do need more space for tomorrow. As many of us know, we're working on systems. Well, we as a human race, working to put systems into orbit that are going to help us progress, help us address a lot of our future issues, future needs. And so, granted, we're going to need more space.
The problem of space debris is not something completely new. What really made the difference at some point was the collision between the Cosmos and the Iridium satellites in 2009.
That collision between those two objects created 2,000 debris. This was the first big collision, and it woke us up.
We have been studying a mission to remove debris for the past 10 years. We have developed concepts, we have developed technologies. The point is that you need to put all of this together and fly it to demonstrate to everybody that it can really be done, because the difficulties come when you put everything together and you really do it. So the ClearSpace 1 mission is fundamental to demonstrate worldwide that we can remove debris.
We are currently working on ClearSpace 1, a mission to remove a defunct object from Earth orbit, and that program will build the fundamental technical building blocks that we will then be able to apply to a wide variety of in-orbit services.
At that point, it will be a tilt. the operators will have suddenly the opportunity or the possibility to remove their satellite once they are non-functional anymore. That did not exist before.
And if we can do what we do today, is because before us, there were a generation of pioneers in the space industry that did miracle after miracle. I think it's our turn today to make the future of this space operation sustainable. And this is what wakes us up every morning. This is why we work all the working hours we do, because we believe that we can bring this change. Today's the day to actually do it.
So as Luc mentioned, really, today is the day that we have right now for all of us to go about this whole process. So as you saw, Luc is the CEO, co-founder with Muriel. Muriel's the CTO. The CTO. Luc, Tim McClay used to be the CTO. He's now Chief Strategy Officer. But between Luc and Muriel, their, I think, respective vision has really pulled in and helped create the culture. Right? We've talked a lot about the culture, leadership, internal processes. For us, the culture has in large part, again, been driven by the leadership team, the co-founders, in such a way that, I think as Joe just mentioned earlier, everyone in ClearSpace is invited to participate, to contribute. Everyone is actually received, listened to. So we've got teams that are filled with some of the brightest minds, at least that I've ever worked with. And sometimes those meetings take a little bit longer than they might have been planned. We are a startup. We're probably not necessarily a startup anymore. We're more in the scale-up mode. But that's just a part of our growing pains, I guess, if you will. But the fact that ClearSpace is bringing this vision forward, ClearSpace is working with our partners. I'll explain a little bit more on a few charts later. Our whole subcontractor environment and ecosystem is a little bit unique. But it literally flows down from these two and the early team. So how did this actually come about? Go back to about 12 years ago, 13 years ago, SwissCube. So Muriel spent about 15 years at JPL at Caltech, up to about 2005, came back to the EPFL, one of Switzerland's kind of MITs, basically. There's one in Zurich, there's one in Lausanne, and quickly kind of threw herself into this domain of sustainability, of looking at what we can do to clean up some things, of just starting to wrap her mind around what this issue was. With her team of students, they created the SwissCube CubeSat 10 by 10 by 10 satellite that they launched directly into the Cosmos 2251 and Iridium 33 debris field. So that, as Muriel, as you saw in the video, that conjunction event created more than 2,000 different debris articles. Most of them trackable, but nevertheless, from 2 to 2,000. Those are the kinds of events that are going to, that are foreseen to potentially occur, and that we're literally going after, full throttle with others, of course, as well. We're not the only ones doing this, but really to address those issues and to avoid that from happening. So launched into the debris field, conjunction events from NORAD indicate all the time. It's still up there, actually, so amazingly enough. That led then to the establishment of the ClearSpace 1 initiative that was, I think, primarily kind of an academic, institutional, informational initiative to begin informing and begin developing active debris removal technologies to address the problem. A few years later, ESA established, instantiated the ClearSpace initiative that looked, the image on the far right over there kind of was one of the technologies that could have been foreseen for this type of work. That initiative then launched the ITT that 3 people at ClearSpace when they initially started, and then 7 when they won this 86 million euro program, unheard of, basically, back in 2019, 2020. So we're roughly 75 or so people today, but back then, 2 years ago, almost 100 million euro program through the CleanSpace initiative, and ClearSpace got on the map, and now, oh my goodness, now what do we do? So I was fortunate or not there at the time. Bastien, who's a colleague of mine, was, and things were not quite as they were today. They were far more dynamic, far more, a lot more, I think, sleep loss probably in those early days, because they were just a very small team, startup, addressing a problem that had barely, I think, hit the radar of most governments. And when I say that, I'll explain a little bit later what I mean by that. So Muriel's story, again, as I mentioned, Caltech, JPL, came back to EPFL, really kicked this off. Met Luc. Luc was originally from the Lausanne area, engineer by trade, went to Stanford's, I think it's their business school, got his MBA, worked primarily in the software industry, a lot of time in South America, South and Central America. They came together and they both had a common vision, and then they brought this vision forward. We address a number of different domains. So when you imagine a non-cooperative target, no matter the size, and developing a system to go up and literally not just meet up with it, but actually dock or capture or remove that object, a whole slew of technologies are required. Technologies, engineering, operations. So we pretty much span the gamut from sensors, navs, robotics, all the way to operations. We're humbled, I think, in the sense that if I start from the end, so from operations, we're looking at systems that are less traditional than most of us have operated spacecraft in the past. It's going to be a cloud-based system. We are, yes, still nevertheless reliant on stations on ground, of course, but the whole operating principle of the mission ops, the mission control center, is a bit of it's a bit of an evolution as to how we've been doing this in the past. We've got some great partners in that. Moving back a bit, so design and integration, I'm just working backwards just to kind of back up from the image of capturing the Vespa or other targets as to laying the groundwork for what's going to be required for this. Those system level capabilities are a large part of where we also incorporate valley space, because all that requirements management, all the downflow, all the analyses and trade space work goes into a huge amount of that design and integration activities. We are currently today planning on integrating our own spacecraft downstream for the ClearSpace 1 mission. We are not physically integrating it ourselves, so we have partners for that. But nevertheless, there will be a hip-to-hip, shoulder-to-shoulder work. I mean, teams, essentially, ClearSpace teams that are going to be working hand-in-hand with our partners to do that. The only reason why we're not doing that is that essentially at the very beginning, ClearSpace being just very few people, we had to decide how to do this. So literally, we went out and we secured subcontractors across the ecosystem, across the European ecosystem that were actually contributing to the program. It's even a little bit more distinct, I guess, if you will. But we couldn't really do it any other way. So we'll be working hand in hand with the integrator. Propulsion, robotics, navigation, sensors. These are areas that are vital for any RPOD, rendezvous, prox ops, and docking activities. We work those in ways such that in the ClearSpace 1 program, for example, we will take all that knowledge, all that experience, And even though we may have other kind of parallel programs, as we saw, Joe discussing kind of this modular approach, we will also, by their very nature, kind of modularly architect these other services that we're going after. We have other programs in the pipeline, very actively engaged across both the European spectrum as well as the UK, and then very shortly as well on the US side. So really enabling core technologies, system-level capabilities, across most of which Valley Space helps us out in the process. Quick overview of where we are today. So we're hitting kind of the 80 employee ceiling here very quickly. This is kind of a snapshot of about 10 days ago. More than 60 proven engineers, talented engineers from all different walks of life and companies, anywhere from Beyond Gravity, Orbcomm, Tesla, ESA. So really a wide spectrum. A couple of our U.S. colleagues are in the are from Orbcomm directly. So Tim and another colleague of ours who's on the West Coast. We've got folks in the U.S., in the UK, in Switzerland, Germany, France. So pretty wide, pretty distributed network of team members that, yeah, we managed this, again, very well. We didn't start, I guess, right during COVID, but we were hit with it very shortly thereafter. So came up to speed really quickly and worked with that. We have other offices planned, but that'll be for another conversation. This is the spacecraft, less of an artistic representation, but really more straight from a CAD drawing. So what you see differently here on the arms themselves, you don't see the beta cloth that you saw in some of the other images. Beta cloth is not only protective, but it's also an electrically dissipative material. So the arms themselves are relatively straightforward. Obviously, we try to keep it simple, but sometimes simple is also the most challenging. The Vespa can be captured in multiple different manners. So this just shows one representation of how we might have approached it and then docked with it. And when I say approach, so imagine this element. It's 150 kilos. It's got a number of kind of protruding elements on it. Not very nice things. Metal, they can do some damage. It is tumbling at a certain rate. It's tumbling at anywhere from, say, 5 to maybe 15 or 18 degrees per second. The process that we took, basically a design process to mitigate a lot of mechanical issues, I mean, basically compromising the structural integrity of not only the arms, but the spacecraft in and of itself. Providing easy access, modeling what the actual capture scenario could be, kind of drove us to the design that we have. It's not a robot arm, but it's literally just a capture system that is going to enclose the Vespa in whichever relative position that we decide in such a way that it will then capture, close prior to contacting. So again, I may not be explaining this very clearly, but when you're traveling at more than 17,000 miles an hour, your approach velocities are going to be very low, very small, very they're going to be minimized to such a point. But nevertheless, there's still a whole lot of uncertainty as to when this capture is actually going to occur and how it's going to occur. And so a lot of what I showed you before, some of those core capabilities, go into the intelligence of how this is going to be done effectively. Bearing in mind that we're not able to create additional debris. So some of you might think, oh, what happens? You come up. I mean, this isn't the first capture that's ever been done. Intelsat, Bird, and Space Lab did this in the early, I think late 90s. It took them about 9 different attempts. They came up and they literally hit the spacecraft. I don't know what came off of it. Don't know I don't think most people do, but they clearly created some debris. We do not have that option anymore, right? It's a sustainable, it's a net sum, net zero sum pledge that we have made, such that anything that we go after, this program and all future programs, we're not creating additional debris. So, let's see, what can I say more about that? The payload itself, so I guess if we want to just imagine the structure of the satellite itself is where a lot of the intelligence lies. The payload, as we often kind of relate to it in traditional terms, is the whole capture system. And it's roughly around 650 to 700 kilograms wet. So we'll be launching it in a Vega mission in 2026. And I think that's probably good. So some of the execution challenges that we have on this, as I mentioned before, so the uncooperative capture, that has not yet been done. We had the choice of a range of vehicles, of bodies that we could go after, anywhere from NVSAT to some smaller masses and anything in between. We chose something that was a little bit more moderate, a little bit more accessible to us, a little bit, something that we could feasibly and reliably go after. So the Vespa, this 150 kilogram mass, was one. NVSAT is another target that is going to need to be removed. It's one of these massive objects like rocket bodies that are going to, if there is a conjunction event, create just a massive debris field. So that will be one of the targets eventually downstream. But because of its very nature, the uncooperative nature of it, there are hugely complex operational phases and onboard intelligence required to negotiate this. Some of the other challenges, we do not know many of the material properties and the structural integrity of this body. It's been up there for 10 years. ATOX, radiation, other detrimental forces over the last 10 years have created whatever environment is going to be available when we pick this adapter up. When we capture it, it may be brittle, it may be less brittle. We really don't know today. So that's one of the huge uncertainties that we have that we need to analyze and design for. The orbital trajectory, as we saw, I think yesterday, Bill presented some scenarios where it's not just in the same trajectory. It does move, it does migrate, and it migrates over time due to solar cycles. It migrates over time just due to potentially drag effects and other lesser important factors. But it is never in the same place where you expect it to be. So that whole orbital trajectory process is going to be relatively developed. One thing that we have tried to do, so just in this target data challenge, is that due to the nature that we don't have access to the material properties, people basically don't want to provide it. We are beginning to kind of have that conversation, open the conversation such that a clause be entered in the contract, either with ESA or with the service, whoever it is that we're going up to support, that there's manufacturer's information on the target, on the relevant debris object itself. That doesn't exist. Like I said earlier, people are very hands-off. I mean, governments are hands-off, operators are hands-off. No one today, even though they follow IADC guidelines to remove debris within 25-year lifetime, none are mandated or could be penalized, if you will, for not doing that. So that conversation also is being entertained, not obviously on the negative kind of penalty spectrum, but really to get people to step up, get governments to step up, operators to consider this in their business cases. Another execution challenge, we've got multiple subcontractors, and when I say multiple, it's dozens. The extensive procurement ecosystem that we have, as a startup, small company, there was a lot of management challenges to just stay on top of that, procurement challenges. The requirements management was a huge challenge that our use of ValleySpace has helped to a tremendous degree, so thank you. However, it's also brought up some other, kind of another theme that has been discussed over the last day or two, last day and a half basically, is this aspect of digital continuity. There are a number of different packages that we could be using it, and they don't all communicate very effectively one with the other. So we do have to kind of, jump those firewalls, go back in, bring files in, bring different formats, across those fences. So that's something that we and others that have presented, over the last day are facing. And I think the last is the extensive client engagement. So by client engagement, I chose not to put the word consumer. Our partner or client is the European Space Agency. They are could be technically considered a consumer of our service. So we provide the service to them. Their engagement is very extensive, I'll say. I'll just put it that way. It has brought a lot of advantages to us in the sense that we've been able to ask, well, they've asked, and it's prompted questions on our end to really ask, in their mind, maybe some of the known unknowns, some of our minds, the unknown unknowns as to what it is we need to be thinking about to successfully realize this mission. Nevertheless, it's far from a commercial approach, right? We don't have product specs. I mean, we have very traditional top-down, flow-down specs to deliver this service. And I keep calling it a service. It's a mission, yes, but it really is a service. So that extensive client engagement, when I heard Joe talk about what how they do it at SpaceX and Elon, we are way on the other side of that spectrum today with this program. So that's that is where we're at on that side. We're working to improve that, and I can guarantee you that that's going to be improved over the next couple of programs, even in this one. So just a couple of quick things. One, I mean, a lot of use cases that we have for ValleySpace I could have gone into. I think just primarily kind of threads or themes that have been vital for us, right? The balance sought that we have been very agreeably surprised and just have welcomed with open arms. Basically, the data robustness and the user friendliness of this system, of the ValleySpace system, has really helped our processes, really helped our approach, helped a lot of the younger engineers come on board and kind of invited them into an ecosystem that 5, 10 years ago, 20 years ago was really complicated. Single source of truth, that's been mentioned a couple of times as well, right? We've got all of our engineering data, standards and requirements, test procedures. We're working to streamline and really seamlessly flow our test procedures, basically operational tests, mission ops through ValleySpace, and that's beginning to flow very well, very seamlessly. As I mentioned, kind of the data exercise across the ground segment operations. We're like I said, we're taking a little bit different approach than many have done in the past. Cloud-based approach, very lean, and so far it's been working really well. We're really pleased. We've got almost 3,000 different components that we're tracking, almost 33,000 different requirements across multiple programs. We have a number of stakeholders, so many external stakeholders, and then a vast majority of our engineers have access and use ValleySpace nearly on a day-to-day basis. So clearly there are needs and use cases for evolving the capabilities, evolving the interfaces, evolving, promoting, I guess, future features, I guess, that we can incorporate it as our programs evolve. And by that, I think for us, what's going to be vital, this is all focused on an institutional program, ClearSpace 1. ClearSpace was not developed to basically drive toward institutional programs. It is a commercial service company that we will eventually get to. This is part of the process of it. But once we get into that commercial service phase, then we start working on more of this column on the right, where the metrics and the processes and the interfaces and the engagements are vastly different than what we're accustomed to and what we're doing on CS1 today, right? I mean, take risk tolerance. You know, clearly, in any commercial operation, any commercial service, that risk tolerance, the risk aversity, is far different than in an institutional program, right? I mean, we're working at 4 nines or 5 nines reliability. You can't do that and provide a cost-effective service. Testing, processes, exactly the same thing. They're essentially, you know, at opposite poles of one another. These are the challenges that we operate under today for CS1, but these are, and as we look forward for our whole commercial service systems in the future. There's going to be a phase where there will be a lot of pain to basically transit from one to the other, but it's going to be very well received in the sense that we're burning down a lot of this risk today on the institutional programs. Today, the next 5 years, the next, say, 7 or 8 years on a couple of these other programs. Those risks get burned down, that non-recurring gets retired, so that as we transition to a commercial service, both for in-orbit servicing as well as active debris removal, as well as potentially future downstream for on-orbit servicing, assembly and manufacturing operations, it's going to be more, I mean, it's going to be a seamless operation. It's going to be seamless transition, because that really is where everyone in ClearSpace, you know, that's where our mindset is. We've accommodated this institutional program for obvious reasons, but that right column is clearly where we are headed, where our target is, where our focus is. And again, like what Joe just presented, I think was just phenomenal. Really, you know, inspiring in the sense that speed is of the essence. Speed, quality, and performance. Some of the challenges and opportunities, I think, you know, for us, again, going forward, and it's really, I think, no surprise to most. I mean, an evolving process with flexible tools, right? We use Valley Space from anywhere from brainstorming the trade spaces into low fidelity model developments, and then extending that into, you know, CM and AIV, AIT, and flight ops. We've been able to, within our AIV, AIT domain, for example, we transitioned the AIV, AIT lead from one of our colleagues in France to a colleague of ours who is very remote, who lives in Guadeloupe, actually. So she was with us for 2 months this past summer, but seamlessly transitioned into the environment that we basically need that new team member to adopt and become fluent with very quickly. So I think it's, you know, clearly a, you know, attesting to the ease of the Valley Space system, the Valley Space, you know, software tool that permitted that transition. Effective comms with external stakeholders, right? I mean, it has served us very well, right? With that, like I said earlier, and we've got 75 plus users of Valley Space in our company. Many of those are external. They see what we see. We can share. We can export. Obviously, they don't have access to everything. We've only provided access to what they need, but nevertheless. And then internally, like I just kind of alluded to in AIV, IT, right? The effective and seamless comms with our internal stakeholders. So our team members can literally flow in, flow out as need be, with very little ramping up, very little onboarding into the system, which is, you know, for us, just phenomenal. Optimizing data localization, basically securing that repository, and then you know, securing the engineering, PA, procurement, and execution buy-in. And I think with that, I've got like 25 seconds. Some of our institutional partners, anywhere from Portugal, we have a great team who are working in Portugal that's supporting our flight software development. Anywhere from also from Poland to the UK to Germany. The top three, I guess, if you will, contributors to this program as the ESA mandated program were Switzerland, the UK, and Germany. So we have relatively large budgets, I guess, attributed to within those countries, and then the rest are somewhat evenly split across other contributing nations. I think one of the perspective from Omega's CEO, who is one of our sponsors, basically an elite sponsor or partner, is really the ClearSpace initiative. It's one of the most important, inspiring, and exciting projects since the launch of the Apollo missions. They've been on there for 50 years, 50 years plus. They've decided to come on again. So we're extremely excited and really humbled by that. So I think with that, I think that was the last chart. I'll just leave you with what we anticipate seeing as we approach the target one day soon, very soon, in a couple of years' time. And I think with that, open it up for any questions.
Well, thank you so much, Fred. It's a really, really important mission, and I wish you all the best and success in being successful in bringing things back down to Earth. We have some small time for a quick question, if anybody has one. I mean, I've got a million questions, and I could stand here all day asking you one, but maybe one that I will ask is, so I've heard that in the possibilities that we have to bring down some space debris include things like lasers, harpoons, nets, I've heard, and many other sci-fi possibilities. Why did you go for the quad arm approach? The approach of the four arms.
So as I mentioned, it's one of the more straightforward, simpler approaches, right? I mean, KISS, keep it simple, stupid, excuse the impression, but we've really tried to approach things in that framework. Harpoons, nets, yes, they could be feasible. They provide massive reaction forces. They perturb the spacecraft itself, the servicer. You might miss. You might create a lot more debris with a harpoon. The net may not function. A lot of things. I mean, just take the example of JWST, for example, right? They had more than 50 different single-point failures on deployments. That's a $10 billion program. They could afford to take the time to make sure that those single-point failures work. This is not that level, but should a net not function? Should the release mechanism not, what do you do then? Well, then now you've got this big thing up there that is going to be non-functional. So we've gone to the capture system itself. Other ways, perhaps different servicing missions could perhaps take that context and maybe architect it in a slightly different way. Maybe you'd have 3 arms, maybe you might have 5, maybe you might have 3 or 4 with a robotic arm, right? Just as an arm itself, just a single. So it was really more the mission, the trade space, the analysis and really overall simplicity and I think elegance of something like this that lends itself perfectly to the target.
Great. And you just quickly, you mentioned something there about cost, and I've seen the cost of this single mission to bring this piece of debris back down, and it's not cheap. Okay, so are there ways, are you at ClearSpace thinking in your processes at an early stage, ways of how in the future this cost can come down and come down dramatically? Because if you're trying to shape sustainability beyond Earth, you also need to do this in a financially sustainable way too.
Yes, absolutely. The institutional missions are primarily not too cost effective. They serve a lot of different purposes. One is primarily to burn down a lot of engineering risk. So yes, it's roughly 100 million euro program, first of its kind. The next program like this, you could probably imagine on the maybe 40 to 50 million, right? So divide that by 2 and then kind of go from there. There are a number of factors that increase the cost of this mission. One, as I mentioned, it's the institutional nature of it. We have client engagements that are very extensive, right? We could, and initially the vision was to actually not proceed down this path in institutional fashion, but it was really to do it in a super lean, very streamlined fashion. Heavy co-engineering, right? Resident engineers with the subcontractors that we defined, that we found, that we secured, that were on board with the same vision that we had. Just going to that approach, I think probably 100 million could have been 15 to 20 million, for example, right? If you provide kind of a risk-sharing context into the equation. Essentially, the more you go toward this commercial service, right, the more you're going to adopt an architecture, be it financial, be it engineering, be it whichever it might be, that is going to streamline, minimize, kind of speed up a lot of these processes. We have months and months and months of between reviews, which, as we all know, really don't lend themselves to anything like a streamline. You've got marching army costs. You've got just all these things kind of add. So, as I mentioned, it is a commercial, right? We are a commercial service company. We're headed in that direction. Obviously, we're going to be exploiting a lot of, I think, what we know, what we've learned, what has been presented so far. I think again, I go back to Joe's presentation. A lot of great, great kernels, great, ideas that Elon has brought forward into his companies that we are definitely going to be exploiting as we go forward.
Excellent news, and again, good luck. And for anybody that does want to ask questions to Fred, then a coffee break is coming up after our next guest, so we can do it there. Again, thank you very much, Fred Baker.